Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. We are still in the data link layer chapter, and in the previous video, we talked about the Hamming code. The Hamming code was an error correcting code. So if we use the Hamming code, the receiver can correct single errors. So if the receiver receives a bit sequence and the receiver applies the Hamming code, of course, assuming that the sender has applied the same Hamming code, the receiver is able to locate the position of the single error. So the receiver would be able to say that the error is in bit number 11, as in the example that we have seen. Or alternatively, the receiver is able to say that the error is in bit number 9 or bit number 3, and so on. So by knowing the position of the error, by knowing the location of the error, the receiver can just flip the value of the bit, so the 1 becomes a 0 or the 0 becomes a 1. It means that we have corrected the data since we're using binary transmissions and we have only 0 and 1. Now, error correcting is nice, but we have noticed that it needs a lot of check bits. So have you seen how many data bits we have here in the example that we solved last time? We have 7 data bits. For the 7 data bits, we noticed that we needed 4 check bits. That's a lot of check bits. So this is a lot of redundancy that we have to add, because the check bits at the end of the day are not part of the data, but they need to be added so that we can correct the errors. For 7 data bits, we needed 4 check bits. But if we use like an alternative example, if we use the single parity bit method, just an even parity bit or an odd parity bit, we're adding just 1 bit at the end. So using that 1 bit at the end, we can detect, we cannot correct errors, but we can detect 1 or 3 or 5 and so on, an odd number of errors. So that's why in general, what we want to say is that error detection is also sometimes important in the case that we cannot really afford adding that many check bits to do correction. So before we start with an actual error detecting code that is called the cyclic redundancy check or cyclic redundancy check CRC, before we talk about that as an error detection example, error detecting code example, let's just have a quick comparison between when is it useful to use error correcting codes versus error detecting codes. Now, what is the trade-off between the two? We have noticed that error correcting codes need a lot of check bits. Error correcting codes need a lot of check bits, which means using up more bandwidth of the network, more basically available capacity of the network, while error detecting codes need less check bits. On the other hand, error correcting codes allows the receiver to correct without asking to retransmit. So what is the trade-off here? We say the following. In communication channels that have a high error rate, so the probability of error is really high. In the extreme example, imagine that whenever I send a frame, there will be an error. In that case, using an error correcting code is useful. So I can afford basically adding those many check bits so that we avoid retransmitting the whole frame again. So that's the case in channels with a high error rate. Like in wireless communication channels, for instance, it might be useful to use an error correcting code, and whenever we send a frame, we add sufficiently many check bits so that the receiver can correct on its own without asking for retransmissions. However, when the error rate is much lower, like in low error rates, like in copper wires and fiber optics, errors do not happen that much, so the probability of error is much less. So every once in a while, we might see an error. In that case, it does not make sense to use the error correction, because error correction means that with every frame, I'm adding a lot of check bits. So in this case, if we have a low error rate, if we have a channel, communication channel with low error rate, it makes sense to use error detection. So with every frame, I just add a few check bits for error detection. And once in a while, if there is a frame with error, the receiver will just ask to retransmit this particular frame. So the whole deal is going to be better. So I just wanted, so the main take-home message here is that both error correcting codes and error detecting codes are useful. Error correcting codes are useful in communication channels with high error rates if we are expecting a lot of errors, but error detecting codes are useful in channels with low error rates, like in wired channels in general, like copper wire and fiber optic. And since error detecting codes are important after all, so they are useful after all. It makes sense to talk about a famous example, which is actually part of the Ethernet standard. So our Ethernet, which is a standard for building local area networks, uses cyclic redundancy check codes, CRC. So how does CRC work? The main idea is as follows. The main idea of CRC is that any data frame, any bit sequence, a k-bit frame or a k-bit sequence can be regarded as a polynomial. So let's look at this example. Imagine this bit sequence, 110001. It's a bit sequence, so it's a sequence with 1, 2, 3, 4, 5, 6 bits. This bit sequence can be represented as a polynomial. How? Simply, each one of these bits is a coefficient in the polynomial. So that's easy to do. Let's start with the least significant here. So the 1 is the basically the coefficient of x to the power of 0. So we start with x to, we are creating a polynomial, so the least significant is a constant, x to the power of 0, multiplied by 1 because we have 1 here. And then the next x to the power of 1 is multiplied by 0 because this bit is 0. X to the power of 2 is also multiplied by 0 because the next bit is 0. X to the power of 3 has also a 0 coefficient because this bit is equal to 0. And then finally, x to the power of 4 and x to the power of 5, each one of these two terms is multiplied by 1 because the first two bits are 1. If we just simplify by getting rid of the 0 terms, it can be seen that the polynomial, so if we think of this bit sequence as being little m, let's call it little m as the bit sequence. Capital M of x is the polynomial that corresponds to this sequence, is equal to x to the power of 5 plus x to the power of 4 plus 1. So what is this polynomial in relation to the bit sequence? That polynomial basically has coefficients which are the same as those bits. So x to the power of 5 is the most significant term. It has a 1. X to the power of 4 is the next term. It has a 1 as the coefficient, and then x to the power of 3, x squared, and x are not available because of these 3 zeros. And then finally, we have the constant 1 because the least significant bit is 1. So mainly, any bit sequence can be represented as a polynomial. Now, how do we use this polynomial in this error detecting code? We say the following: the sender and the receiver agree upon a polynomial that we call the generator polynomial g of x. And from the first bullet, we know that that generator polynomial g of x can also be represented as a bit sequence. So sender and receiver agree on a generator sequence, a generator binary sequence, or equivalently a generator polynomial g of x. Now, what is the significance of using this generator polynomial? The sender uses the generator polynomial g of x to generate the check bits, to calculate the check bits. Then the sender will append the check bits to the data bits and then send. Now, when the receiver receives that received sequence, it will use the same generator polynomial to check whether there are transmission errors or not. So this is the deal. Sender and receiver agree upon the same generator polynomial. It has to be the same as part of the protocol. They use the same generator polynomial, and we know that the generator polynomial is also equivalent to a generator sequence, a generator binary sequence. That generator polynomial is used by the sender to create or generate the check bits. Once these check bits are appended to the data, the whole thing is sent as a transmitted sequence. When that sequence arrives at the receiver will use the same generator polynomial to decide whether there are transmission errors or not. Let me add the following. Let R be the order of the generator polynomial. Now, the order of a polynomial is the highest power. So this polynomial, x to the power of 5 plus x to the power of 4 plus 1, has an order of 5. Okay, so the order of the generator polynomial represents the number of check bits that we are using. So if this is the polynomial we're using as a generator polynomial, it means that we're using 5 check bits. So the sender will be calculating 5 check bits, adding them to the data, and then the receiver will use the same generator polynomial to decide whether there are transmission errors or not. Now, as a piece of information, that generator polynomial has some conditions so that it is really able to detect errors. The simplest condition, so the bottom line condition is that this generator polynomial must start with a 1 and end with a 1. As a binary sequence, it must start with a 1 and end with a 1. In other words, the most significant term and the least significant term cannot be zeros. Both of them should be existing so that the generator polynomial is able to detect at least a single error. Now, proving this is beyond the scope of this course. It needs some abstract algebra that typically engineering students did not study. However, we mention it as a fact. So if the first term and last term are zeros, then it will not work. An example generator polynomial of degree 4 is shown here. G of x, x to the power of 4 plus x plus 1. So this is an example generator polynomial of degree 4 or of order 4, which means that if this generator is used, it means that we have 4 check bits involved. So the sender is calculating 4 check bits, adding 4 check bits to the data, and then sending the whole thing. And the receiver will also use the same generator polynomial to decide whether there is an error or not. Now, this is also useful. So using the generator as a polynomial or as a binary sequence is equivalent from the first bullet. So whether we say capital G of x as a generator polynomial is equal to x to the power 4 plus x plus 1, or little g as a binary sequence is 1, 0, 0, 1, is equivalent. I think you can easily convert this polynomial into a binary sequence. X to the power of 4 is available, so we have a 1. And then we don't have x to the power of 3. We don't have x squared. That's why we have 0, 0 as coefficients. And then finally, the constant 1, so we have a 1 at the end. So whether we have a polynomial, we can easily come up with a corresponding binary sequence, or if we have a binary sequence, it is easy to find the corresponding polynomial. Now, bottom line again, if this is the generator polynomial, x to the power 4 plus x plus 1, or equivalently the generator sequence 1, 0, 0, 1. If this sequence is known and agreed upon between sender and receiver, what does the sender do with the generator? It uses that generator to compute the check bits. So in this case, the sender would compute 4 check bits, add the check bits to the data, and then send. Now, when the receiver received its received sequence, it will use the same generator polynomial or generator sequence equivalently to detect if there are errors or not. Now, in the following example, I will show you how this works. So I think the best way to explain how it works is by using an example right away. In this example, assume that the data, we are at the sender side. So I'm the sender and I have some data that I wish to send to a receiver, and that data consists of 1101011011. This is my data I want to send. In addition to the data, I know what the generator is. So the generator sequence is given. So it has to be given, of course, because it needs to be agreed upon the sender and receiver. So the generator sequence is 10011. As a polynomial, it's easy to convert, even going backwards from the least significant. So we have a 1 here, which means we have the constant 1, or equivalently 1 times x to the power of 0, or just 1. We have another 1, so the next term x is available. 2 zeros means x squared and x cubed are not available. And finally, x to the power of 4, which indicates that the order of the polynomial is 4. And the order of the polynomial, by the way, is always the number of bits minus 1. So 1, 2, 3, 4, 5, minus 1. That's the order simply because this is a constant term. So this is a constant term, and then x squared, x cubed, x to the power of 4. So that generator has order 4, and it means that we are using 4 check bits. So what does the sender do? The sender wants to, using that polynomial, it needs to calculate 4 check bits, add those check bits to the data, and then send the whole thing as a transmitted sequence. This is what happens at the sender. Let's finish that off, and then we will also talk about what happens at the receiver side. Now, the sender calculates the 4 check bits by using polynomial long division. I trust that you have seen it somewhere, but let's review it. Polynomial long division, we are dividing the polynomial that corresponds to the data by the generator polynomial, right? But doing this division, we need to consider the coefficients only. So at the end of the day, let's write the data that we need to send here: 1101, 011, 011, here 1101, 011, 011. That's the same as the data. However, before we do the division, before we divide, since we know that we will have check bits, 4 check bits, since we know that we will have 4 check bits, and this comes from the order of the generator polynomial, initially at the center side we add 4 zeros to the data bits. I'm putting those in red. So what we divide at the end is the same as the data, in addition to 4 check bits. Why 4 zeros, sorry, not check bits yet, in addition to 4 zeros. Why 4 zeros, not 3 and not 5? It is simply the number of check bits. We have 4 check bits, so initially we add 4 zeros. So the polynomial that corresponds to this sequence, which contains the same as the data as it is, in addition to the 4 zeros, is divided by the generator polynomial. Do you see the generator polynomial? The coefficients are 1, 0, 0, 1, 1. I'm putting here 1, 0, 0, 1, 1. So what do we divide? We are dividing this polynomial by that polynomial using polynomial long division. Let's do it together in this video, and this is the whole workout. So how do we divide a polynomial by polynomial? We take the first coefficient, which happens to be a 1, and we divide it by the first coefficient here, which happens to be a 1. So what is 1 divided by 1? 1 divided by 1 is 1, so I put it on top. Obviously, what you see here is the quotient, so it's the result of the long division. So 1 divided by 1 is equal to 1. Once I get this 1, what do I do with it? I take this 1 and then I multiply by the full generator sequence. 1 times 1, 0, 0, 1, 1 gives me 1, 0, 0, 1, 1. So what you see here is this 1 multiplied by the generator. It gives me 1, 0, 0, 1, 1. And then I put a line and I subtract what you see here minus what you see there. Subtraction is modulo 2 because we have only binary numbers. So modulo 2 means 1 minus 1 is 0, and 0 minus 0 is 0, 1 minus 1 is 0, and 0 minus 1 is also 1. 1 minus 0 is 1. 0 minus 1 is also 1. We don't have negative numbers. It is just 0 and 1. So by the way, this subtraction is equivalent to doing an XOR operation. But it's easy. So let's subtract. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. 0 minus 1 is 1. So until here, I finished subtracting. And then what do? Do you see this arrow? The rest of the sequence, I take it as it is here. 1, 1, 0, 1, 1, and the 0. So I took the rest of the sequence so that I divide again. I will start from here. I finished this bit position already. That's why that 0 that I got, I will not use it to divide or anything. So that's why I took it out like this. And I go to the next. You see the highlighted one? I go there to this one, and then I repeat the same division again. 1 divided by 1 is equal to 1. That's the second bit in the quotient. It's equal to 1. What do I do with it? I take this 1 and then I multiply by the whole generator. So 1 times 1 double 0 double 1 is 1 double 0 double 1. And then I subtract. I subtract again. Sorry, that 1 multiplied by 1 double 0 double 1 is 1 double 0 double 1. And then I put this line. I subtract what you see on top minus what you see underneath it. And this by coincidence gives us all zeros. So 1 minus 1 is 0. 0 minus 0 is also 0. 0 minus 0 is a 0. 1 minus 1 is a 0. Another 0. And then from there, the arrow, I just copy everything down so that I don't get confused with the bit positions. Okay, that first 0 is taken away exactly as I've done here. Because I divided this position already, I will not divide again. So I will not divide. This is taken away. And then I go to this 0 and I divide. What is 0 divided by 1? It's a 0. That's what this third bit is in the quotient. Okay, if I go slow motion, I can take this 0 and then I multiply by the generator, which will give me zeros. And then when I subtract, it gives me the same thing. So in the special case, I'm getting a 0 here. In the special case, I'm getting a 0 here. We can also take the bit away and we go to the next. So we save time and space. Now we go to the next bit. It's also a 0. 0 divided by 1 is a 0. And then I take it away. Next bit, 0 divided by 1 is a 0, and then I take it away. 0 divided by 1 is a 0, and then I take it away. And now I'm done with all my zeros, and my next bit to divide is a 1. So let me take that 1 divided by 1 gives me a 1, right? 1, and then this one multiplied by the whole generator gives me again 1, 0, 0, 1, 1. And then I put the line and I subtract. As in the previous two steps here, I subtract. 1 minus 1 is a 0. 0 minus 0 is a 0. 1 minus 0 is a 1. 1 minus 1 is a 0. And 0 minus 1 is also a 1. And then do you see this arrow? The last 3 bits, I just copy them and put them here so that I can just work with this line and I forget everything on top. Now, that bit position, as we have done in all these steps, that bit position is already finished because I divided this one already, so I will not divide that 0 again. I go to the next, which is a 0. I go to the next, which is a 0. 0 divided by 1 is a 0 here. And I don't need to multiply. If you multiply, as I said before, if you multiply, it just gives a 0. So if you subtract, it gives you the same thing. So let's just work with the same line then in this case. So that 0 was divided by 1 in the quotient. It gives me this 0, and I take it away. Sorry, I take it away. So I go to the next bit. The next bit is a 1. The next bit is a 1. 1 divided by 1 is a 1. 1 divided by 1 is a 1. And then 1 times the generator gives me 1, 0, 0, 1, 1. Let's put the line and subtract again. 1 minus 1 is a 0, which we take away because we don't need it. So always take away the first after subtraction. The first one is done, and then we consider the rest. 0 minus 0 is a 0. 1 minus 0 is a 1. 0 minus 1 is 1. 0 minus 1 is also a 1. And then that last 0, do you see the arrow? It goes down. So what we have now is 0, 1, 1, 1, 0. Okay, we have still one bit position that we have to deal with, which is this 0. Why do we have to deal with an extra bit position? Because so far we have 1, 2, 3, 4, 5 bits, and we're dividing by 5 bits, by 5 coefficients, so we divide one more. Bottom line, we keep dividing until the remainder at the end is less than 5 bits, basically 4 bits, and this is what we need precisely. If you get less than 4 bits, if you get 3 bits, for instance, it means that we have a 0 to the left so that we make them 4 bits. Now, we divide that 0. So again, let me go back to the subtraction. We subtracted these two lines. We get a 0, which we take away, and then we have 0, 1, 1, 1, 0. Since these are 5 bits, 1, 2, 3, 4, 5, I take this 0 and I divide. 0 divided by 1 is that last 0 in the quotient. And because this is a 0, let's save time. As I mentioned twice, let's not multiply because it will give you the same thing, and subtract. And subtract, you will eventually get the same line here. So since we get a 0 in the quotient, we just take this 0 away, which means that I'm left with 1, 1, 1, 0. 1, 1, 1, 0 are 4 bits. 1, 2, 3, 4. So that's our remainder. As long as I have 4 bits, which is less than 5, it means I have a remainder, right? I have a remainder, and this is the most important task. This is the most important piece of information that I will use to proceed. Now, this was the original data sequence. I added the 4 zeros, and then I divided by the generator. I got a quotient on top, and I got a remainder at the bottom. The quotient is not used. The quotient is not used. I just need it so that I get the correct remainder, but the remainder is used. Now, how will I use the remainder? Here we say the remainder is 1, 1, 1, 0. What do I do with this remainder exactly? What I do is that I take the original sequence. I take the original sequence, including the zeros, which was 1, 1, 0, 1, 0, 1, 1. This was the data. And then I put the 4 zeros as they are, and then I subtract the remainder. When I subtract the remainder, I get the same data as it is because I have zeros here. I get the same data as it is, but I get the check bits at the end, which are the same as the remainder. So bottom line, although I'm subtracting the data with the zeros minus the remainder. I'm subtracting the data with the zeros minus the remainder. What happens is that those zeros will get replaced by the remainder. Let's try to subtract. 0 minus 0 is a 0. 0 minus 1 is a 1. 0 minus 1 is a 1. 0 minus 1 is a 1. And this is as it is because I'm subtracting 0 from it. So what happens, that subtraction operation is equivalent to putting the data as it is, followed by these 4 remainder bits. So these 4 remainder bits are actually the check bits. So what is the transmitted sequence? What is the transmitted sequence. By the way, I just noticed that we have a typo here. So when I put these data bits, here, it's supposed to be the same as those, but it seems that I forgot some of them. What you have here is actually the same as the data bits followed by the zeros, so it's supposed to be the same as this line. But this is correct. What you see here is correct. So after that subtraction, or equivalently replacing the zeros with the remainder, what we have is the transmitted sequence. So what does the sender transmit at the end of the day? The sender transmits the data bit with the check bits, and the check bits are exactly the same as the remainder bits. Now, what did we gain by doing that? We have introduced a very nice structure. As a homework, take that sequence as it is with the check bits. So 1101, 011011, the data with these check bits. Take that and divide using polynomial long division by the same generator. Take this bit sequence, so take those bits as they are, which include the data and the check bits, do a polynomial long division by the same generator. If you do the same long division, of course, what you will be dividing is not the data with the zeros. No, it will be the data with the check bits. If you do the same division, you will get zeros at the end. So what we can say is that this new sequence, which contains the check bit, is divisible by the same generator with no remainder. So this is always the case. So once the sender calculates the remainder and then replaces the zeros with the remainder to create the transmitted sequence, which contains data and check bits, that transmitted sequence is always divisible by the same generator with no remainder. And this can be used by the receiver as a certificate. And this leads us to the receiver algorithm. So how does the receiver work? The receiver works as follows. It takes the received sequence. Of course, if the receiver receives this sequence with no error, it will receive exactly the same. So 1101, 011011, followed by the check bits 1110. If the receiver takes that sequence and divides by the same generator 10011, using exactly the same way, do it as a homework, you will find that the remainder is just equal to 0. This does not give us a remainder. However, what happens if the received sequence is not the same as the transmitted sequence? So some of these bits change, one or more of the bits change, we get a transmission error. That received sequence with errors, if it is divided by the generator, it's supposed to give us a non-zero remainder, and that allows the receiver to detect that there is an error. So let me give you an analogy so that you are convinced why this works. So what is the main idea here? Again, let's review the main idea. So the sender took a polynomial which has some zeros at the end, and then it divided by a generator polynomial, and we obtained the remainder. And then the remainder was subtracted from the original sequence. And this is the outcome of the subtraction. Of course, as a special case, the outcome of the subtraction is equivalent to removing the zeros and putting the generator bits, putting the remainder bits as they are, but at the end of the day, this is still a subtraction. Now, let's do an analogy. Of course, in the actual CRC method, we are doing polynomial division, but as an analogy, it's not exactly the same, but it's similar. Imagine that we are dividing decimal numbers. Imagine that we're dividing 9 by 4. So 9 divided by 4. What is 9 divided by 4 using the remainder method? 9 divided by 4 is 2, and remainder is equal to 1, because 8 by 4 is 2, but we have one more in the 9, so the remainder is equal to 1. If I take this remainder, 1, if I take this one remainder and subtract from the 9, so 9 minus 1, that's the original 9. 9 minus 1 is 8. Now that 8, if you try to divide by 4, it can be divided with no remainder. And this is the philosophy here. So we do a polynomial long division. We take our data followed by the zeros. We have 4 zeros in this case because we have 4 check bits, because we are using this generator polynomial, which is given. I take my data bits followed by the zeros. I do a polynomial long division by the generator until I get the remainder, and the remainder has to be 4 bits, simply because we have 4 check bits and simply because we divide by 5 bits. Now, I take those remainder bits and then I subtract them from the original sequence that I divided, and the result will be the transmitted sequence. I think you should be convinced now that this transmitted sequence, if I try to divide it by the same generator, it gives me a 0 remainder. It is divisible. So this is the structure that was added by the sender. The sender makes sure that any transmitted sequence, regardless of the data, because we get a suitable remainder here that we use as check bits so that the whole thing is divisible by the generator. If the receiver divides by the same generator, it gets a 0 in case it receives the same sequence as it is, because the transmitted sequence is divisible with 0 remainder. But if this changes during transmission and the receiver receives something else, if the receiver divides, it will get a non-zero remainder, and this is what the receiver uses to decide whether there is an error. So this is the same example that I have used in my illustrative slide here, and this summarizes the receiver algorithm. The receiver will receive the received sequence, divide by the same generator. If the remainder is equal to 0, it will conclude no errors. If the remainder is not equal to 0, it will conclude that some transmission errors happened, one or more. We don't know how many. We cannot even locate them. The CRC is an error detecting code. Now, as a matter of fact, the cyclic redundancy check method is used in the Ethernet standard. Ethernet is a standard for wired local area networks, and that CRC method is used. So this method with polynomial long division is actually used in CRC. It is used in the Ethernet standard, and one of the famous Ethernet standards is called IEEE 802.3. You maybe know that 802.11 is the Wi-Fi standard. 802.3 is one of the famous Ethernet standards, and that particular protocol, that particular standard uses cyclic redundancy check with the following generator polynomial. So it's fixed. Whenever we have an Ethernet transmission, the sender is using this polynomial to generate the check bits, and the receiver is using the same polynomial to check whether there is an error or not. So as you notice, that generator polynomial is of order 32, which says that we have 32 check bits. It says that we have 32 check bits. As we will see in a future chapter, if you look at the Ethernet frame structure, you know, the Ethernet frame starts with a header, and then comes the data or the payload, and then there is a trailer at the end. The trailer contains the check bits, and we have 32 of them. So this is the generator polynomial. It can be shown, and again, the proof of what I say here is beyond the scope because it needs some abstract algebra. It can be shown that using this generator polynomial guarantees that any burst of errors, you know, a burst of errors means errors in consecutive bits. So an error in bit number 5 and 6 and 7 and 8, so errors one after the other. We call that a burst of error. All bursts of error of length 32 bits or less. So 32 errors after one another, or 31 errors one after another, and so on. 32 bits, 32 errors or less that come in a burst can always be detected using this generator polynomial. So what this means is that if I get 32 errors or less, one after the other, and then the receiver divides by the generator, it will really get a non-zero remainder. And also all bursts of an odd number of errors, not necessarily 32 or less, any number of errors that are odd, so 1 or 3 or 5, or 33 or 35 or 101 or 1001, any odd number of errors that appear as a burst, one after the other, can always be detected using this generator polynomial. So this is just a piece of information that comes from practical networking, and this will conclude this lecture, and we will continue next time with retransmission strategies. Assalamu alaikum wa rahmatullah.